So as we move into chapter 18, and as we discuss this potentiometry, like I said, we sort of did a little bit about it on Monday. And we talked about this electrochemical cell here. This is what we call a passive cell. We're not applying any voltage to it. We're just putting our setup in some solutions and seeing what comes out of it. Some of the potentiometric probes are passive, but the vast majority of them are not. The vast majority of them are powered in some sense. Right. So so in a passive cell, the current comes only from the system. Okay. We're not going to get too deep into this, but we call these the half reactions. You did a good bit of this in Gen Chem 2, right? I know it's been a while. But these are your electrochemical half reactions. You pair up reduction with an oxidation, right? So our zinc here is getting oxidized, our copper is getting reduced. We just have to make sure that the same number of electrons are passing from one side to the other. Okay. We looked at this table of standard reduction potentials, and we looked at this equilibrium quotient, Nernst equation. First edition books, man. In all of these equations, somebody copied and pasted. It has IN. This is not indium, right? We know this is the natural law. I don't know. I mean, yeah, just know that it should be LN, natural log. I didn't fill this in. I noticed that I didn't fill this in, right? But when we do Q, right, it's always products over reactants. Hopefully you remember that, but I don't know why I didn't put it in on Monday. Okay. I like that our textbook calls this a flashback to Gen Chem 2. This sort of triangle between the standard potential of the cell, the equilibrium constant for that reaction, and then the Gibbs free energy for that reaction. And we have these relationships that relate all of these guys, and we look mostly at the Nernst equation, which is this one. They give two versions here because if we sort of combine RT and F into one factor, we get this 0.0257 volts out of it. Okay. It's fine with me if you want to use that, but you have to be at 298K in order to do that. The R for this one, right, we're going to use the 8.314 joules per mole Kelvin. And then, of course, Faraday's constant is 96,500 coulombs per mole. That's related to the number of moles of electrons and the electrical charge for one electron. There's probably some more sig figs out there somewhere, but 96.5 is what I always remember. Okay. All right, so I erased my notes from this pH probe, and I got rid of the ion selective probes, because I wanted to talk about it a little bit more. Okay? The energy, not the energy, sorry, the cell potential that we see is equal to the potential of the cell. And for us, when we use these combination electrodes, that's equal to the potential of the indicator electrode minus the potential of the reference electrode. I said this perhaps less eloquently on Monday when I was talking about how we hold one of those two containers like we think about in a galvanic cell. If we hold one of those at a constant value and the other one fluctuates, then we can calculate what the difference is and calculate some concentrations and things like that. And so this reference cell is what we hold constant. Now, the reference that scientists have sort of set at E equals 0 is the standard hydrogen electrode. Well, we'll take a look at that in just a minute, but it's a very complicated electrode to actually run. Not only are you making hydrogen gas, which goes boom, but in order for it to be a standard hydrogen electrode, the pressure of that hydrogen gas has to be 1 atmosphere. The concentration of your acid has to remain at 1 molar as you run your experiment, which of course is going to convert some of that, is going to react with some of that acid. And so in reality, the standard hydrogen electrode is kind of a lousy electrode to use as a reference. Almost always, we use a silver chloride reference electrode, which, just for your own information, has an E naught of positive 222 volts. And that's what we compare everything else against, right? And so if we again take a look at this pH probe that's sort of blown up for us here, our solution, our interior solution that we have, this electrolyte solution, is going to be a saturated KCl. So it's going to be we need that Cl minus. So let me write out this reaction: AgCl solid plus an electron give me Ag solid plus Cl minus. Okay. So for this to be truly a standard, the nice thing about this is silver chloride solid doesn't participate in our equilibrium constant. Silver metal solid doesn't participate in our equilibrium constant. This chlorine minus does, but as long as we keep it a saturated solution, that concentration shouldn't change, right? If we have a little solid KCl at the bottom, if we use up any of that Cl minus, it's going to be replaced by some of that KCl that will dissolve. If we have any extra Cl minus, it's going to precipitate out because now we're over our saturation threshold. And so this electrolyte solution is a saturated KCl solution. Right? And so let me see. Well, we'll talk a little bit more about that reference electrode in a bit. But again, we have our, this is a nice pH probe because it has a built-in temperature sensor, right? So it can plug in whatever temperature the actual solution is at, rather than just assuming that it's going to be calibrated at 20 or 25 degrees C. For a pH probe, we want to maintain a neutral pH inside our membrane. Right? And so that's why we have this buffer that's going to be at 7.0. Right? So we maintain our pH. This is also why it's very important when you're using pH probes and when you're done using them to put them back in that buffer, right? I don't know if any of you have TA'd for labs that have pH probes, but at the end of the lab, you always put your pH probe back in that little container of solution. The reason is so that if we, depleted some H plus, or if we have extra H plus, it can buffer it back out, and we'll get back to that pH of 7 inside our probe. So we'll talk a little bit more about pH probes in particular here in a minute, but this is that combination electrode where the reference and the indicator are part of the same setup. Okay. So here's the standard hydrogen electrode. This is what I was talking about, how you have to have a constant pressure of hydrogen gas. You have to have a constant concentration of whatever acid you're using. I don't think it has to be HCl, but I could be wrong. I just think it has to be a strong monoprotic acid, because I'm pretty sure that the rule is that it's just H plus, not HCl. But in any case, you have to maintain all of these concentrations, and instead of it being a saturated H plus solution, which is hard / impossible to do, it's 1 molar solution. And so yes, it's equal, it has a cell voltage of 0, but it's pretty lousy to actually operate. The two much more common reference electrodes are the saturated calomel electrode, which was common for a very long time. It's sort of falling out of favor because you see here, it's got mercury in it. Mercury is, of course, a no-no these days. Also has a little asbestos in it. Man, what were they thinking? But this operates very similarly to this AgCl electrode, but just with mercury and mercury chloride. Here we see this saturated KCl mole per cubic decimeter. A cubic decimeter is a liter. Can we just write molar? I don't know what this is about. So what we have is on this silver wire in the middle, right, we form this AgCl on the surface. And so again, we're setting up that equilibrium between that silver chloride and the silver solid, and the chlorine minus. I left off my electron. And so this is the reference electrode that we have in our pH probe. Let me go back just one slide here. Right? So here's our reference electrode. So I'm going to color it in red. Right? That would be our little silver wire right there. And on that silver surface, you get your silver chloride, and that's where your reference potential would come from. Okay. So again, much more common reference electrode, the silver chloride. Calomel is still used, right? It's a relatively, when it's built in as a combination electrode, it's self-contained, and you're not really going to have any worries about mercury contamination. Also, if it's in a combination electrode, then it's going to be such a small amount of mercury that it's really not that dangerous. remember that a combination electrode is where the indicator and the reference are in the um, same probe, right? Rather than it being a separate probe like you see here, where the silver superchloride has its own wire going to it. You'd have to have a separate indicator. A combination just has those two together. So I'll come back. I got these slides out of order. When we look at a pH probe, right, we talked a little bit about how you have this glass membrane, and the protons work their way in. I might have said Monday that they work their way through, right? They don't make it all the way through the glass. But what happens is glass is high in potassium and sodium, just because that's part of the hardening and clarifying agents that they use to make glass these days. They're high in our alkali metals. And so you have a lot of sodium in your glass, and then because it's been in the buffer for a real long time, some of those sodiums get displaced by protons, right? You swap Na plus for an H plus. And so in the buffer, some fraction of our sodium ions have been swapped for protons. Right? Once we put it in acidic solution, right, more of our protons swap out. And this changes the potential across that glass membrane. Right? And so this is what happens when you put your pH probe in your solution. This also explains the reason why pH probes are not instant read, right? They need to equilibrate a little bit because that displacement takes a few seconds to occur. Right? And so our pH probes need that second or two for any ion swapping to occur. Okay. All right. So now I'm going to go back a slide. Like I said, these are a little out of order. Do our equations for our potentiometric stuff. I'm going to rewrite the Nernst equation. Negative RT over N natural log of Q. So that is sort of I missed an E naught. There we go. So this is in an ideal world, right? And while we may teach you ideal world things in Gen Chem 2, we recognize that it's not ideal. And so even maybe at the beginning of this chapter, we convert from E cell to E observed, right? Because there's other things happening, we don't actually know what the cell potential is. We just know what it is when we observe it. Right? we can sort of take this one step further. Because we're using a reference electrode almost always, then there's never the reference concentrations to worry about. Especially if we're using the calomel or the silver chloride electrodes, those concentrations are constant, right? Either if we're talking about the solids, they just drop out. If we're talking about the Cl minus, it's a constant and unchanging. And so we can recast this. So with a reference electrode, we can rewrite this as the observed potential is equal to RT over F times the natural log of our analyte A plus K. Okay. It's the catch-all constant that incorporates lots of things, right? So now he takes into account not only that E0 cell, but it takes into account whatever else is happening that we don't really have control over, that's causing our observed cell voltage to not equal our calculated cell voltage or whatever. And so let me annotate this just a little bit, right? So this is our analyte concentration. And this is sort of our, I'm just going to call it a catch-all constant. Right? Many times we assume that that's zero, right? We assume that there's no real difference between the observed voltage and what the cell voltage should be, right? Is it a great assumption? Sometimes yes, sometimes no, but it's one we tend to make anyway. For pH in particular, we're going to go one step further. Because we know something about the concentration of hydrogen and how that relates to pH. Right? And so, if we convert our natural log to a log, so we can get log of H, because we know log of H is pH, what we end up with is that our observed potential is equal to this constant 2.303 RT over NF times the pH. I dropped a negative sign. Negative 2.303. And then plus our ubiquitous K. And so that constant 2.303 takes into account that switch between natural log and log. And then of course pH we know is log of H plus concentration. Negative log of H plus concentration, which is why we have that negative thrown out front. Our textbook is a little constant crazy. Can I say that? Because they actually, again, take this one step further and make all of this business K1 and turn this into K2, K0. You need to know what this is. We need to know what temperature is. Because we're going to change with temperature. So why make this a constant? This is, don't do that. The reason why they show you this is because a lot of instrument manufacturers that don't take into account temperature do just say, okay, so pH should increase at 57 millivolts for every pH unit. And that's at 25 degrees C, that's in pure water. That takes a lot of things, that makes a lot of assumptions, but they know what that calibration curve should be. And so then they can just make that K1, whatever that correct value is. So it's not ideal, but I prefer leaving it out as those variables. Okay. All right. So we'll do one little problem here, and then we'll go for today. So this is a big crazy equation. Yeah. What this equation shows us is that we talked about how protons can swap out those sodium atoms, right? Because they're good at doing that because the charge is much more dense, right? Remember, a proton is the size of a nucleus with a positive charge versus sodium, which is the size of an atom with a positive charge. And so being a more dense charge, it can sort of, sneak into that glass a little further, displacing some of those sodium ions. Other metals, however, can also displace those sodium ions, right? Or displace the hydrogen that's already in there. And so what this term is, right? This is, well, it's just this F bit here, right? This is the selectivity coefficient. Right? And essentially, it's how well do other metals swap out hydrogen. Right? So if we're measuring pH, we want the hydrogens to join in that glass layer, that glass membrane. But if other metals are doing that, that's going to affect our pH. Right? And so we have this selectivity factor, and actually this still has, this in terms of log of H plus, and I feel like I dropped a negative sign, but it's not in the textbook either. I feel like there should be a negative sign in the front. I'll do some research and let you know on Friday. Not in our textbook. So, but this can be simplified because we know the connection between log H and pH. We can sort of take the electricity part out of this, take the voltage part out of this. When you say the pH is equal to the negative log of this business, right? H plus this sum of those selectivity factors times the concentration of each ion. Plus K. Can't forget our K. I guess this should be a parentheses. Okay, so knowing that, given that ocean water is 0.47 molar sodium, right? We're going to calculate the area and pH. So we're going to assume that it should be neutral, right? We're going to say that if ocean water were neutral, what pH do we get if we assume that K is equal to 0? And I gave you the selectivity coefficient there for sodium. We're also making the assumption that sodium is the only thing in ocean water, which it for sure is not, but it's the biggest bad boy. What's H plus when the pH is 7?
1 times 10 to the negative 7th.
There we go. And we get a pH of? What did Russ get?
I haven't gotten anything.
I got 6.95.
Hey, 6.95. Excellent. Okay. And so because there's other positively charged ions in our solution, our pH probe doesn't really know the difference very well, and it just knows that there are other things that are moving into and out of that membrane. And so it responds accordingly and says that our pH is lower. Is it a huge difference? No, it's not terribly different, but it's enough to change our result. All right, that's where we'll stop for today. We'll finish up with these slides. Well, there's only one more slide, but we'll finish up with that slide and then talk a tiny bit about voltammetry, chapter 19 stuff on Friday. Okay, have a good one.
See ya.
Dr. Davis.
Yes.